Okay, hi everyone. I'm Shannon Danforth from the University of Michigan. Absolutely thrilled to be kicking off Dynamic Walking 2019. And this is work with Patrick Holmes and Ram Vasudevan on inverse optimal control with sit-to-stand data. So researchers have investigated optimality in human motion using a number of different tools. We've seen the use of simple models to find optimal gaits, which we can then compare to what we observe in humans. And also a tool called InverseOptimal Control, where we can take a set of human data, say locomotion, and assume that this data is the result of some optimization problem, and uncover the objective function that's associated with this set of data. And we've seen inverse optimal control with seated posture and arm manipulation, but not yet sit-to-stand, which is what I'll be talking about today. So our sit-to-stand experiment involved 11 healthy subjects. First, the subjects performed nominal trials where they stood up from a comfortable foot position using their natural strategy. And next, the subjects shifted their feet forwards and then backwards in 2-inch increments. Once we have our data, we build individualized pendulum models. So these models have two states, angular position and angular velocity. We'll call our state vector x. And we have an input u that's applied at the pendulum base. So with this data and model, our goal is to uncover some function of our model states and inputs that is minimized by this set of data. And to do this, we used a problem formulation for inverse optimal control developed by Edward Powles. Some key properties I want to highlight is that we are recovering a polynomial cost function, and we can specify the degree. We solve this with sums of squares optimization, which allows us to find a globally optimal solution. And once we recover this objective function, we can then use it to generate control inputs for simulation. So let's see what a degree 4 polynomial cost function looks like for all of our 11 subjects. There's a lot going on the x-axis here. We have every monomial that appears in a degree 4 cost function for a pendulum model, and then the weights on these monomials on the y-axis. And right away, we notice that across 11 subjects, these cost functions look really similar. Which is interesting, but let's see how well these cost functions work in simulation. So here is a subject's foot-shifted sit-to-stand trial where we have position, angular velocity, and input. And what we're going to do is take all of the subject's other trials and use them in inverse optimal control and simulate the left-out trial. So we see, great, it looks like it matches up pretty well, reaches standing, but we'll quantify this by computing error between simulated and real data, and then doing this across all subjects and computing a normalized root mean square error in position, velocity, and input. So since these subjects looked similar, all their cost functions look similar, we also used an intersubject leave one out. So this was, can we take a subject and use other subjects' cost functions to simulate their data? And in doing this, we again get a simulated trajectory that reaches standing, but across all subjects, we notice a larger error, especially in the angular velocity and input space. And lastly, we decided to compare this to a cost that wasn't found with inverse optimal control that said, let's just reach standing. So this cost function has weights that are shown in the red dots here when compared to what we found across all subjects using inverse optimal control. And using this standing cost, we found that we had a much larger error in position, velocity, and input. And we can visualize that error as well. Here's the standing cost error, and the intersubject leave one out error, and the smallest of all, which is using subject-specific cost functions in a trial-by-trial leave one out. So that's the end of my 5 minutes, I believe. We use inverse optimal control. 1 more minute? Wow, okay, we can stretch out this conclusion. So across 11 subjects with our sit-to-stand data, we noticed that the cost functions looked very similar using this inverse optimal control formulation. However, even though they look really similar, it ended up better if we used a subject-specific cost function than using other subjects' cost functions to simulate the left-out subject. And then both of these inverse optimal control leave one out analyses performed better than trying to use a cost that just said get to standing. So that's it, and I'll take any questions.